Now, question 2 shows you an example of what an infrared spectrum from an organic compound might typically look like. So this is just my sort of sketch of the one that's there in the question paper. So remember that the peaks are these things pointing downwards here. So this is a strong peak, somewhere around sort of 1700 wave numbers, in between 1500 and 2000. And what makes infrared useful, or the first thing that makes it useful, is that once this technology was developed and people started running spectra of lots and lots of compounds, they started to notice patterns. And in particular, they noticed things like every compound that contains CH bonds has a cluster of peaks like these in the region of 3000 wave numbers. And eventually people worked out that that was because CH bonds, when they're made to vibrate, always have the same sort of energy required to excite that vibration, and therefore that will always occur at about the same wave number range. And you don't just get one peak, you get a cluster of peaks, because there are different types of CHs and they can also vibrate in different ways, but they're always clustered around that region. And so you can learn to recognize, oh, that peak is due to CH. Now that of course isn't very helpful if you're trying to get clues as to what the structure of an organic compound is, because nearly all organic compounds contain CH. So unless you're trying to exclude the possibility of it being, you know, like a compound where all the hydrogens have been replaced by fluorine or something, you know, except in those very special cases, that's not particularly helpful vibration, but it's one that you need to be able to identify. Similarly, they noticed that that very strong peak there, around 1700 wave numbers, occurs whenever you have a carbonyl group, C double bond O, in a compound. And again, they worked out that what's happening when you absorb at that particular wave number is you're making that C double bond O stretch. And that's extremely helpful, because if you see that, it's very strong evidence that there is a C double bond O in your molecule. Equally, if you run a spectra of something and it's flatlining through there, you can be very sure there isn't a C double bond O. And that can be just as useful as knowing that there is one. So looking for absences of characteristic peaks in infrared spectra is actually just as useful as looking for their presence. Now, the thing that's incredibly useful to you is that you don't actually have to memorize particular peaks, because they're all listed for you on your data sheet. So if you have a look on your data sheet, it's directly underneath the bit which lists, you know, Avogadro's number and all those general values that you need to know. There's a table of the characteristic infrared wave numbers. So what you need to do is to use that table to learn to identify specific peaks. And I say in this particular spectrum, the one that should leap out at you is the carbonyl peak in the middle there. That's right in the middle of the spectrum. It's always very strong, and you don't really get much else anywhere near it, so it's not very likely that you're ever going to confuse it for anything else. Nevertheless, for this peak, as for any other peak, you shouldn't just say, oh yeah, that's roughly in the right place, so I think that's C double bond O. Okay, because I say you're not very likely to make a mistake with that one, but with some other ones you can do, just by sort of looking at it and thinking, yeah, that looks vaguely right. You've got to do it properly, and what that means is that if you think that's C double bond O, you've got to look at the range it gives you in the data sheet, and you've got to check that it really does occur in that range. So it tells you in there C double bond O is expected at 1630 to 1820 wave numbers. So what you do is to take some kind of set square or similar, so I'm using some Ravel, other composers are available, and what you do is you just put this along until you come to 1630 wave numbers, and you just draw a line. Just sketch it on there like that, and check that that really does bracket the peak, and then the same at the other end. You come to 1820 wave numbers and you slide this along till you come to 1820, and again you draw a line, making sure it's square. That's why it's important to use, you know, a book or a set square or something like this to make sure that you've got this right. And then you draw that line down there, and it should approximately bracket the peak like that. It may clip the peak somewhere, you know, down towards the bottom or something, and some peaks like the CHs tend to wander around a little bit, so they won't always be contained within that envelope. But if your peak is actually outside that envelope, so if it's really, you know, the tip of the peak is out here somewhere, then you think that really doesn't look like C double bond O. So that's something you should get in the habit of doing. Just do that with a square edge of some kind and check that the peak really is in the right place. But if you do that on the one in question 2, you find that that is indeed C double bond O. Okay, so we think, yeah, we've got C double bond O. The question also asks you to find any OH peaks, because again, infrared is very good at picking up OH peaks. And if you look on your datasheet, you can see that there are 2 different types of OH peaks. There's the carboxylic acid OH, so the OH that's part of that group, and that gives a peak that it lists between 2,500 and 3,300 wave numbers. And then there's an alcohol OH, so something like that, for example, but it doesn't have to be primary, any kind of alcohol OH, or a phenol. We haven't met phenols yet, but again, a phenol is a compound where it's connected to a benzene ring, which we'll learn about next year, but that's what a phenol is. So you can see they're different from carbonyl groups because from carboxylic acid groups, because they don't have the carbonyl adjacent. And those give peaks in the range of 3,200 to 3,600 wave numbers. And both of those are in relatively empty parts of the spectrum, so again they're easy to interpret. So we'll look for those in a minute, but let's just look at some of the later spectra to see what those actually look like, and then we'll come back and see whether we think there are any here. So spectrum number 2 actually shows you what a carboxylic acid spectrum looks like. And again, the important thing to be doing is to match it to the datasheet. Don't just kind of look at the general shape and think, oh yeah, I'll remember that, because you've got to make sure that the peaks really do correspond to the right places. So on your datasheet it tells you that a carboxylic acid OH gives you a peak in the range 2,500 to 3,300, which is a very broad range. But if we just find that on here, so 2,500 is somewhere around there. So if we draw the line up, you can see that comes sort of somewhere there. And 3,300 comes sort of somewhere here. You know, can do this for real on the spectrum, actually print it out, and you can see that it, again, it doesn't go right to the bottom of the peak, but it basically brackets that huge broad peak pretty accurately, and so that fits. That's what you expect for a carboxylic acid OH. You can see that it swamps the CHs, and you can see them there as little sort of spikes on the shoulder of this peak. So they are still there, but they're just kind of superimposed on this massive OH peak. So that's what you expect for a carboxylic acid OH. But again, don't just do it by eye. Draw these lines on there, make sure it really is in the right range, and that's how you make sure you don't make mistakes in assigning peaks. Of course, because it is a carboxylic acid, the structure of COOH contains not just that OH peak, but also C double bond O. So that means we should have not just the OH peak, but the C double bond O peak. And we already know where to look for that because that was what we had in spectrum 1. So remember, it's 1630 to 1820 wave numbers expected. For that. And if you go with your right angle thing, make sure that you're marking perpendicular to the axis. So 1630 should come somewhere sort of around here on your actual spectrum, and 1820 comes somewhere over here. And so again, you can see that that peak does fit, you know, fairly squarely within that bracket. So you can be pretty confident that that's C double bond O because it matches that, and that this whole broad thing here is a carboxylic acid OH because it matches that, and you put the two together and that's a carboxylic acid. It gives you the molecular formula, which is something very simple, C2H4O2, and if it's a carboxylic acid with two carbons, there is only one possibility, which is that it would be that. Okay, spectrum 3 looks a bit like this, and this time the standout peak is this big one here, because you can see if you compare that with spectral 1 and 2, you haven't seen anything like that in either of those. And if you look at your data sheet, what you'll see is that what that matches is what you expect for an alcohol OH, as opposed to a carboxylic acid OH, which is different in infrared. So again, if you get your right angle, your data sheet says alcohol OH should be about 3,200 to 3,600, and so if you do that on your spectrum, mark on the line, you should get something that looks sort of like that at that side, and then something, you know, like this here. So again, the peak fits within that prescribed window that corresponds to an alcohol OH. So that's a pretty clear identification. Obviously there isn't a carboxylic acid OH as well. There aren't enough oxygens for that, but even if there were, you can see there aren't, because these sharp peaks, remember, here are the CHs clustered around 3,000, but there's nothing extending down towards 2,500 like we had in spectrum 2. So even if you didn't know there was only one oxygen there, you would be confident there was no carboxylic acid there. And equally, there is absolutely nothing. You can see around 1,700 where we had those strong carbonyl peaks in spectrum 1 and spectrum 2, it's now flatlined there. So that tells you that because there is nothing there, you know that there is no C double bond O. And say that negative evidence is often just as useful as the positive evidence. You know, knowing what there isn't in the molecule can be just as useful as knowing what there is quite often when you're trying to piece a structure together. So what we've got from that is that it's an alcohol which fits that formula, and obviously again, because it's such a simple thing, there's only one candidate, which is that that's methanol. So now that we know what OH peaks look like, it's worth just looking back at spectrum 1 again. So we had already identified the C double bond O peak. Right, so remember that with your set square thing you had verified that that fitted in the expected range of sort of 1630 to 1820. So we knew from that there was C double bond O, and because there's only one oxygen in the molecular formula, in this case you would know there can't be an OH because that's the oxygen accounted for. But obviously in general the molecule is going to be more complicated than that, or you may not even know what the molecular formula is. So it's important just to check that there are no OH peaks. But now that you know what they look like, you can see that's clearly the case. If there were an alcohol OH peak, remember it's 3,200 to 3,600. So it comes to this side of the CHs. These, remember, are the CHs. Make sure always to check that those are there clustered around the 3,000 mark, because unless it's a weird organic compound where all the hydrogens have been replaced, you know you're going to have those peaks there. So we're not really interested in those. But if there were an OH, you would get a peak sort of around there, like that. And it's, you know, it's a strong peak. It's just got this very smooth shape, and it clings fairly closely to that range, 3,200 to 3,600. As I say, ignore the little things like that. That's not what we're talking about here. We're talking about a big strong peak. So no, there clearly is no OH there. From an alcohol, what about a carboxylic acid? Well, 2,500 to 3,300, but remember that doesn't just mean somewhere in that range, so don't look at that and think, oh, that comes within that range, so that could be carboxylic acid. It really means it fills that whole range, so it's going to go all the way down to 3,300, which is here somewhere, and give you a great big strong peak, kind of something like this. It usually looks like. Okay, so it's massively broader than anything in that spectrum. And again, if you just get your square edge out and just hold it along the 2,500 line and just say, right, does my peak come close to that? And the answer is clearly no here. So you know for sure that there's no carboxylic acid. So what is spectra, or what is compound 1? Well, it's got a carbonyl group and it's only got 2 carbons, so there is actually only one possibility again, which is ethanal, which is that, okay, which fits the molecular formula and fits the spectrum because it has just the carbonyl group there. Spectrum 4 you may have spotted straight off just by comparing it with spectrum 2 and seeing how similar the peaks at this end are. You might have thought, oh, that's a carboxylic acid again, but don't rely on that visual similarity. Remember, you must check the actual ranges. So if it's a carboxylic acid, we're going to expect a carboxylic acid OH, which is 2,500 to 3,300 wave numbers, and we're going to expect a carbonyl group, which is 1630 to 1820 wave numbers. So if you're going to say, yes, I think this compound is a carboxylic acid, you have to demonstrate that it has both of those peaks. So again, you get your right-angled device out and you just sort of say, right, 2,500 to 3,300, where does that come? So it's going to be somewhere sort of there, and here. Put that on there. Okay, so that fits, okay, because that huge broad peak is coming within that range, so that's carboxylic acid OH. And here, this is the carbonyl peak. Again, we have to check that it fits with 1630 to 1820. So you put your straight edge there and find that indeed it does. So you get something like that and you say, yeah, that's C double bond O, because it fits that range as well. So yes, that's convincingly a carboxylic acid, and because that's the formula, it has only one carbon, so again there's only one possibility, which is that that's methanoic acid. Okay, one carbon, so it's meth. So methanoic acid is what's giving you that spectrum. Question 5 then looks a little bit like this, and the peak that probably grabbed your attention straight away was this huge strong peak in the middle, which you've now seen several times, and you'll have thought that looks like a carbonyl peak. But remember, you mustn't jump to that conclusion until you have checked the actual position. So 1630 to 1820, if you put your square edge on there and mark that, then you find that it comes sort of there and somewhere like this. So yeah, that fits nicely. So you say, right, that looks like C double bond O. When you're writing down actual exam answers, it's important to show you're working like that, to identify the group, but also to quote the data sheet, to actually write down 1630 to 1820 cm to the minus 1. So when you're writing down, explaining how you've used your infrared evidence, it's actually quite important to make sure that you write down both what you think the bond is that's vibrating, that corresponds to that peak, and how you know that by quoting the numbers from the data sheet. These peaks clustered around 3000, you know, are CHs. In general, you're not going to get asked about those because almost everything's got CHs, so they're not really interesting. Just make sure you don't confuse them for anything else. And there can't be any OHs because there's only one oxygen there, so that must be the carbonyl one. But again, you can see clearly from the spectrum that there aren't any, because if there was an alcohol OH, it would be looking something like that, and you can see there's nothing like that. Again, there's a bit of something in that part of the spectrum. You know, it's not dead flat, but just ignore those small things because there could be all kinds of reasons for them. They're not interpretable. And if it was a carboxylic acid, you'd have a huge broad peak spanning this sort of range, not this much narrower CH thing. So again, it's clearly not carboxylic acid. So all the infrared tells us is it's got a carbonyl group, and we know the molecular formula is C4H8O. And this time we can't figure out exactly what it is just from that, because you should be able to find 3 isomers which have that molecular formula and which contain a carbonyl group. So if you have a straight chain of 4 and you put a carbonyl group on it, so the simplest thing would be to put it on the end like that and make an aldehyde. Then if you count the hydrogens, you've got 3, 4, 5, 6, 7, 8. So that fits. So that's C4H8O. You could also make your straight chain of 4, but put the carbonyl group in the middle and make a ketone instead of an aldehyde. So we've got butanal or butanone, and those are both possibilities. And it says there are 3. So we can't just keep moving the carbonyl group along, because if we moved it to there, that would be the same as this, and if we moved it to the end, that would be the same as this. So those are the only 2 possibilities if we have a straight chain. But of course we don't know that the chain is straight. We could have a chain of 3 with a branch on it, and there's only one way to put a carbonyl group on that. Can't put it in the middle, because that carbon would then have 5 bonds, so that's no good. But it could go on any one of those 3 ends, but it doesn't matter which one it goes on. You can see from the symmetry that that would be the same thing. So this compound, which is a different aldehyde, that would be the 3rd one. In question 6, in terms of what we can see in the spectra, it's a similar story to the last one. We've got the CHs here, bunch of sharp peaks clustering around 3000. Always just say, yeah, those are the CHs, so we're not going to worry about those. But then the eye-catching one is the big, strong one in the middle there. So again, just do the check, make sure it's in the right place, but that looks very much like a carbonyl group. So just get your square edge and check, and if you do plot on 1630 to 1820, you should find that that corresponds quite well. Okay, so you say, yeah, that fits for C double bond O. As I say, it's a good idea to quote the data sheet to say how you know that it's that. No OHs, again there's only one oxygen, so there couldn't be an OH as well, but clearly not, because there would be a nice broad alcohol OH peak there if there were an alcohol group, and you'd have this big broad carboxylic acid peak spanning where the CHs are, but it's not, it's nice and sharp there, so that tells you that's not a carboxylic acid either. So again, that's all the infrared can really tell us, is that it's got a carbonyl group. That's the molecular formula. And this time there are several things it could be, and it just asks for a couple of suggestions. It has 2 fewer hydrogens than the compound in question 5. but the same number of carbons. So that suggests that it has either a carbon-carbon double bond or a ring in it, which compound in spectrum 5 didn't have. So first it asks us for an alicyclic. Compound alicyclic just means that it contains a ring. So you could have, for example, a ring of 4 with a carbonyl group on it, and that would be C4H6O, so that would fit that spectrum. Or you could have a ring of 3 with a carbonyl group on it and a branch, so that would also fit the spectrum. Or indeed you could have a ring of 3 with a branch and put the carbonyl group on the branch. So any of those would do as possible compounds that would fit the molecular formula and the spectrum. And so you can sort of see from this that even for quite small compounds where you have only 4 carbons, infrared doesn't tell you what the structure is. It's not that powerful, but it gives you useful clues by telling you something about what functional groups it contains, and as we said, what functional groups it doesn't contain. And that is very useful. When we've learned about other kinds of spectroscopy this year, and particularly next year, you'll see that infrared has a role to play along with other things in establishing what the actual structure of a molecule is, but it can't do that on its own. The other thing it asks for then is a suggestion where, rather than being alicyclic, it has a carbon-carbon double bond, and it specifies in particular that it must have EZ isomers. So, you know, this, for example, would fit the molecular formula, but it wouldn't have EZ isomers because that carbon-carbon double bond has 2 hydrogens at this end, so if you flipped them over it would still be the same thing. So it can't be that, but it could, for example, be this. Okay, so that fits the molecular formula. So you've got C4H6O, you've got 3 hydrogens there, 1, 1 and 1. And that one of course does have EZ isomers because each of the carbons of the double bond has 2 different groups attached. And if you run down there, the priority group is the one with the bigger atomic number of the attached atom, so that's going to be there because carbon beats hydrogen, and there because carbon beats hydrogen, so they're on opposite sides, so that's the E isomer. And you could have this one, which would then be the Z isomer. So that would be the possibility that's an alkene rather than having a ring.